Okay, let's start the second talk. The talk is given by Professor Kwon. He will give us a third lecture on the crystals.
Yeah, thanks for the introduction. So today I will talk about the crystal base of the negative part of the quantum superalgebra. So my notation was use of m/n. And before starting this topic, I want to give some comments on the last lecture where there was there needs some correction. So, okay, the minor one, but anyway, I gave a wrong explanation. So in case of okay, maybe we need better to start with sorry. Okay, so in the last lecture, we considered the CAS module, which can be viewed as a parabolic Volmer module starting from the even part of GLMN. But the good thing is that it's still finite dimensional, and it also has a crystal base, and that crystal base is compatible with the projection to our irreducible polynomial representation. And its crystal structure is also very simple. So as I said, it was the Cartesian product of three sets. And the first two are the crystal of the usual GLM and GLN, which also has a nice combinatorial realization, many realizations. And the extra factor now coming here is the certain the power set of the set of even odd positive roots. But okay, and its crystal structure is also very clear. So when we want to understand it as a GLM crystal, then we consider the first two factors and the tensor product. And for the case of GLN or U0N crystal, then we consider the tensor product, the other two factors, not the other, those two factors in yellow with the reverse tensor product, and also for the odd ones. And in the computation, so here's the example of the computational crystal operators on the first factor, the power set of the positive odd roots. And so we can identify that set as the heuristic data for the multiplicity in the odd root vector. But the odd root vector in the PBW basis only has degree multiplicity 0 and 1. So we can identify that first factor as binary matrices. So in case m by n binary matrices, and the crystal structure for the even simple roots can be described very explicitly. So for example, when we consider the F1 tilde, then we consider only these 2x4 binary matrices. And the wrong comments I did in the last lecture was that basically it can be computed using the signature rule. But here we should assign the sign for the binary matrix 1, 0 to plus and 0, 1 minus. And for the 0, 0 and 1, 1, we just give the trivial sign. So, and then we apply the signature. Okay, so now let's go to the negative part of the quantum group. Okay, so now we know the crystal of the CAS module. And then now we want to think about the whole negative part. Then you can imagine that naturally expect that the way we can do this is take the limit of the highest weight for the GLM and GLN. And it's already well-known fact that that crystal or the crystals for those finite type form a natural directed system, and then we can take a limit to get a crystal of the negative part. So that we can expect that the only natural candidate for the crystal of the negative part is the this set in yellow. So it's the product of the P of pi 1 plus and then Bm infinity and B0 infinity. Yeah, so, but so still we need to describe more precisely what the crystal structure on that set is. Of course, basically, we apply the tensor product rule when it describes the crystal structure for the CAS module. But so it naturally induces somehow the crystal structure. But anyway, in this lecture, we will describe the precise crystal structure on that limit. And one bad thing, or some not how to say. So one thing I have to comment is that the limit crystal is not connected, unfortunately, unlike the case of user Casimir algebra. So it has some finitely many connected components, but still the good thing is that each connected component is actually isomorphic. So we will give a more detailed description for that connected components. And then we consider the algebraic construction of the crystal base of the negative part, which gives the whose associated crystal is this limit crystal. And then we finally talk about our algebraic construction of the crystal base and its compatibility with the crystal base of the CAS module in the last lecture. Okay. So this was the brief review, which I already showed in the first or second lecture. So in case of GLM, the limit system of the crystal of highest weight module is given in this way. That means for two dominant integral weights where mu is greater than the lambda, then we define an embedding of a crystal from B of lambda to B of mu in this way. So if the crystal in B of lambda is given by x v lambda, where x is the product of fi tildes, then we just apply the same crystal operator to the highest weight vector with the bigger highest weight. Then it gives a well-defined crystal embedding, and then its limit, it becomes the B of infinity. So basically, we have this kind of idea in mind and want to apply this process to the case of a CAS module, but some other thing happens here. So let me explain in more detail. Okay, so anyway, in our case of GLMN, so we started from the P plus. It was the set of integral weights which are dominantly integral with respect to GLM and GLM. So it was dominant with respect to even part. And we define the same partial order as in the case of GLM. Okay, so now we want to think about, so we have two weights in P plus, lambda and mu. Mu is bigger than lambda. And we want to think about a map from the B of K lambda to B of K mu. Okay. But I just want to remind you that when you consider the crystal structure with respect to GLN, or the even simple root with the negative squared norm, then the crystal structure is can be described explicitly, but the tensor product order was reversed. So we have to think about the crystal for GL0n first, and then this part. So that causes some different thing compared to the case of usual Casimir. So anyway, I will define this map, say zeta. So suppose that our B is consists of these elements, let's say S, B plus, and B minus. Okay. Then we can say that there are some operators X and Y. So the second factor is from the crystal of GLM, so it can be written like this. X is a product of the operators with even simple roots with a positive norm. And then we consider the the elements as a crystal element with respect to GL0n. Then anyway, still it is a crystal over the usual simple Lie algebra. So it can be written as like this. So this is a 0n maximal weight vector or element. Then there is operator y, which gives this pair. Okay. So we pick up the maximal element with respect to the GL0 U0n crystal. Okay, then we apply the same pair of operator x and y to the triple of the. So here the S0 is come from here, and then we replace the V lambda plus and V lambda minus by the mu plus and mu minus. So we consider the directed system using these maps theta. Then we can check easily that the first, this map is injective and as a set, and its limit is those product. And of course, it's easy to check. There's an embedding of UMN crystal. That means the crystal for the even part. Okay. And basically, we want to say that this map gives also embedding of the crystal over GLMN, but unfortunately, it's not. But still, somehow it is embedding. It's compatible with other crystal operator locally. That's roughly speaking, it's a local embedding. That means, okay, so we have a crystal Cas module. It becomes bigger and bigger if we take the limit of the dominant weights for the even part. So it has a limit. So if we pick up some elements in the limit, then so we can apply the other operator, crystal operators. And then actually we want that operator is compatible with the injective map in the direct system, but it is not true in general. But we can say that if we take the Cas module component bigger and bigger, the element is fixed. But once the highest weight is big, if the highest weight is still big enough, then after that the operator always comes with embedding. So in that sense, it's a local embedding. So that was written rather technically here. Okay. So B is okay. So if B is given by it's a sequence of B nu, where B nu is the component in the crystal Cas module corresponding to nu, then if there is another, okay, so here B prime, so we also consider B prime, so this B nu prime. And then once B is fixed and B and B prime are fixed, and then the lambda is large enough, then there is an arrow colored M in lambda component if and only if there is an arrow M in the mu component. Yeah. So the factor 3 enables us to say that the directed system, the limit has a well-defined GLMN crystal structure. Not only the crystal over GLM plus GLN. So we have a well-defined abstract UMN crystal structure on this set. Okay. Okay, so as we already have seen that the odd crystal operator acts on the first component, just adding or subtracting the multiplicity of the odd root vector corresponding to alpha n. And for as a crystal over GLM0, it acts on the first two components. And actually, it becomes a UM1 crystal because the odd operator acts on this first component. So we can view this first two components as a crystal over UM1, GLM1 crystal. And rather other thing is that actually in the level of a CAS module, when the crystal structure over U0n, then we consider the two factors over there and then apply the tensor product. But if we take the limit, then actually the operators for U0n, it doesn't actually have an effect on the first factor. So that means as a crystal over U0n, we just, the crystal operators just acts on the last component only. Yeah, that causes actually the limit set, and the limit crystal is not connected. But anyway, let us denote this limit crystal by BMN infinity. And it is not connected in general because, for example, the crystal operator for the even part with the simple root with the negative squared no only acts on the last component. So it actually, so it does not act on the first component in the power set. So it has a finitely many connected components in general. Okay, so now, so now I want to describe the connected component, each connected component in this limit crystal. Okay. So for this, let us recall some results, well-known results in the theory of the crystal-based theory in the Casimir algebra case. Okay. So that's actually about the crystal structure when it consider the tensor product of finite dimensional representation and the crystal of negative part. So here is a fact I want to actually use or need to describe the connected component, our limit crystal. So suppose that now we consider the GLM crystal type A. And Bm of lambda is the crystal of the finite dimensional irreducible representation. And Bm infinity is the crystal of the negative part. But anyway, there is abstract crystal structure, and also there is an abstract tensor product rule. So we can take a tensor product to have another crystal. Then, of course, it is not connected, but the connected component can be described as follows. Actually, it's a disjoint union of the crystal where each component is isomorphic to the crystal of the negative part. And there is some shift of weights on the highest weight vectors. And actually, the highest weights can be parameterized by very nicely. It is the disjoint union is parameterized by the Bm of lambda, the tensor product we actually take with this infinite crystal. And the highest weight here is just corresponds to each element of Bm of lambda. And yeah, in my understanding, this can be viewed as a crystal version of the Volmer filtration when you take the finite dimensional representation and Volmer motion. But here you have a discrete version, so it is a disjoint union of the crystal. Okay, so for the later arguments, let me briefly review how it can be proved. So it's basically given in the first paper by Professor Kashiwara and Duke about the existence of the crystal base for the Casimir algebra case. Okay, so we need another algebra, so-called algebra of Q bosons. After that, some people call the Kashiwara algebra, say BQ, and now I'm only consider the case of GLM. So this is the algebra generated by two kind of generators, EI prime FI, parameterized by the simple roots. And of course, we can add some possibly the Cartan part to that algebra when you want to think about the weights of the simple module of that Q-boson algebra. Okay. But anyway, it is proved that for that BQ, there is only one simple module, say V infinity, up to highest weight, if we consider the weight. And also, it is one of the main results was that this simple module has kind of crystal base. This simple module is isomorphic to, first it is isomorphic to the negative part of UQGLM. Of course, we know that the Fi generator acts on the left multiplication and EI prime acts on the left Q derivation. So with respect to that action, UQ minus is a BQ module and it is irreducible. And then we can define the crystal operator, and then it is proved that the A0 span of the one of the main results was that there is a crystal base for that simple module, and actually the crystal lattice is given by starting from the highest weight vector, and we apply the Fi tilde operators finitely many times and consider A0 span, then it gives a well-defined crystal. That was one of the main results there. Then why we need this fact? Okay. Yeah, maybe I will review one more fact. Actually, we need it. So now we consider the finite dimensional representation of UQ and tensor product by the irreducible BQ module. So it is not the module over the same algebra, but there is actually the UQ, the quantum group has the boson algebra BQ has a left co-module structure, so that we can think of the tensor product of finite dimensional representation and V infinity as a module of the boson algebra. So the co-module structure is given like this formula. Okay. So there is an algebra homomorphism from BQ to UQ tensor BQ, where EI prime goes to this kind of element. So it looks a little similar to our usual co-multiplication formula. And for Fi, that goes to this one, it's exactly the same formula in the quantum group case. So under this section, M tensor V infinity becomes it's actually semi-simple. What is good is the semi-simple BQ module, and it is isomorphic to, since it has only one simple module up to highest weight, so it is a direct sum of the V infinities. Okay, so applying this fact, then we can show that the fact which I mentioned. Okay, so one more thing. Yeah, so now finally, there is also tensor product theorem. So if LB is a crystal base of our finite dimensional representation, V infinite has already crystal base, L infinite, B infinite. Then if we take the tensor product, then as a module of a BQ, it also has a crystal base. It is a crystal base of N tensor V, so that it is isomorphic to the direct sum of the crystal base of the V infinity. And finally, the crystal operator, EI tilde and Fi tilde on this tensor product, it's very nicely acts on the crystal, is following the same tensor product rule we know. Okay, so using that fact from 1 to 3, then we can now state this fact. Okay. So B lambda tensor B infinity is now isomorphic to disjoint union B infinity. And now finally we need to decompose or characterize the maximal vectors in this tensor product. And it's very simple. So following the tensor product rule of crystals, then each connected component is completely determined by the highest weight elements. And following the tensor product rule, each highest weight element is given by this form. So first tensor factor is always highest weight. So it's a U lambda. And the second one is not necessarily highest weight, but it has the following combinatorial formula. So EI of B is bounded by the pairing of these two weights. So now we consider the star involution on the second part of the crystal. Then this condition becomes exactly the characterization of the subcrystal of Bm of lambda in B infinity. So we have a natural bijection from each maximal vectors here to each crystal elements in B of lambda. Yeah, so that's the classical fact, but we still need. Okay. So now let me give first a statement of the connected component of our limit crystal. So this is a joint work with my former student Ilsen and a current student with Akito. And first we can prove that each connected component in Bmn infinity, they are all mutually isomorphic, and it is isomorphic to the crystal, which is a Cartesian product of Bm1 infinity and B0n infinity. So here Bm1 infinity means the crystal of the negative part of the GLM1. And B0n infinity is just the GLN crystal. So as a crystal over the GLMN, actually the reason why I use the Cartesian product is that the crystal operator for the GLM1, so the index I is from 1 to m, they only act on the first component, and the remaining, the even crystal operator acts on the second component only. So it acts separately. So the result is that each connected component in our limit crystal is isomorphic to that kind of crystal. Yeah, so somehow the structure is split into GLM1 and GL0n. And also we can compute the number of connected components so that Bmn infinity is isomorphic to this crystal, and the multiplicity is exactly 2 to the m times m minus 1, so that we can say that it is connected. Bmn infinity is connected if and only if when n is 1. Okay, let me give a sketch of proof. Okay. So, okay, so first we did the following fact. So this crystal, which can be also as a crystal over the Castle module with highest weight 0. So now we want to look at this crystal as a crystal over GLM1. Then just at the beginning of this talk, I reviewed briefly how to compute the crystal structure on this power set. So we can compute that as a crystal over GLM1, this crystal is isomorphic to the product of this crystal Castle module over GLM1 with the trivial highest weight and some set C, which is still a binary matrix, but here the condition is that the multiplicity for the other root vector for GLM1 is always trivial. So it is naturally in one-to-one correspondence with, okay, so this means that in the example here that we consider those kind of arrangement of odd root vectors. So this set C is consists of the elements where this first column is trivial. So we can view this as can be identified with the set of binary matrices. The size of the column is strictly smaller than n-1 size. And so this set also still has a crystal structure of gel M and gel m-1. It's a bicrystal structure. Since the rank for the part of N has reduced by 1, so it is a crystal over the disjoint union of the crystal Bm of lambda Bm-1 lambda transpose with the following length conditions. And but if we ignore this part, the crystal structure, then the multiplicity of each Bm of lambda is given by the number of elements in that crystal. Okay. So now we can prove the decomposition or characterization of the crystal. So we start from Bmn infinity. So it is a Cartesian product of these three sets. And then, and of course, when you take the limit, so the crystal structure here was given by taking the limit of the crystal of Castle module, and we observed that the GL0n crystal structure only act on the third part. So we regard this crystal as the product of GL-M1 crystal and GL0n crystal. So now we look at this first factor, and then in the previous slide, as a GL-M1 crystal, you can view it as this one. No, it's no, sorry. It's how to say? Yes, GL-M1 crystal. And, yeah, that's right. And we consider, okay, so we replace this part as this crystal. And then we know that this crystal C can be viewed as a disjoint union of the crystal of GL-M with the multiplicity m lambda. Okay. Okay, right. And then, yeah, then so this crystal can be viewed as a disjoint union over lambda of this crystal. Okay. Yeah, then now we consider, yeah, so this crystal is so the Bm0 infinity. Oh yeah, in the, how to say, so we consider tensor product of this one, right? Right. So applying the lemma, which I just recalled, that it can be decomposed into the crystal of B of infinity, the parameterized B of lambda, right? Okay. Now we can say that the, okay. So now we consider the crystal here, and then actually this part becomes isomorphic to Bm1 infinity. So it becomes, so it is isomorphic to the Bm1 infinity tensor B0n infinity. Okay, so considering the multiplicity, then finally we can say that yeah. So it's a reunion over This union is over the B of lambda. And then we can say that also there is a multiplicity is the will be E0 n minus 1 lambda transpose. Okay, so yeah, considering the skew RSK correspondence, then the whole union is actually parametrized. Okay, so sorry. So the union is taken by this one with the multiplicity. But if we consider the skew RSK correspondence, then we can identify this union, this set, as the set of binary matrices. So its cardinality is this binary set of matrices. So it is 2 to the m times n minus 1. Sorry, yeah. Okay, so that's the decomposition of our limit crystal. Okay. So now we can want to talk about the algebraic construction of the crystal base of negative part. But from the abstract crystal structure, we can expect that how to define the crystal operators on the negative part. Okay, so we take so we want to construct a crystal base L infinite B infinite such that whose associated crystal is our limit, and also which is compatible with the crystal of Casimir-Mojon. So okay, so our lattice is defined. So we define our lattice L infinity by the product of each crystal L of K0 and L of infinity and L of infinity for M and N respectively. But here, so L of K0 means the crystal lattice of Casimir-Mojon with the highest weight, 0. And L M0 infinity is the crystal lattice of U negative, U M0 negative, Q equals 0. But we should be careful when we consider L0 n infinity. So it is the actually crystal lattice of so the P is the minus Q inverse. So it's the crystal lattice at infinity. So so psi is the isomorphism, which I have introduced in the first lecture. So it's just an example of the UQSL to triple. But if we restrict the UQSL to triple for the simple roots with negative squared norm, then the isomorphism with the usual UQSL to triple is given by this form. So the Q equals 0 on the left-hand side corresponds to the P equals infinity. So our natural candidate for the crystal lattice for the GL0n should be the crystal lattice at infinity, P equals infinity. Right. Okay. So we define the crystal operators for for the non-odd roots. We define the crystal operators, and the usual ways. For M0, we define the crystal operator in the usual sense, and for 0n, we also define the crystal operators, but considering the isomorphism psi with the usual quantum group. So it's a little twisted. And the other root operator, the Fm tilde, defined in the same way. So the X on the Fm tilde is the left multiplication, and Em tilde is given by the derivation. And okay. Yeah, so for each I, so the crystal operator Fi tilde on U in U minus is defined in the following way. So there is isomorphism of vector spaces between U minus and the tensor product of the subalgebra K and U minus M and U minus N by multiplication. Then for the even simple root with positive squared norm, we define the Fi tilde to be the one actor on the first two components. And of course, I would like to remark that so this crystal operator actually acts on the module of the Q-boson algebra, which is given by the tensor product of the finite dimensional representation and the infinite dimensional simple module. So in that sense, this operator acts on these first two components. But still is well defined, and we have a well-defined crystal structure. For the even simple root with the negative squared norm, then it acts only on the third component, according to our crystal structure. And the odd root is defined in this way. Yeah, then somehow it is now is straightforward to show that this crystal lattice becomes a crystal base of U minus. Of course, we need the Kashiwara's results on the crystal base theory for the tensor product of finite dimensional and the infinite dimensional representation. So finally, I now still have some time. So finally, I want to talk about this crystal base and the compatibility of this crystal base and the crystal base of Kess module. So in the usual crystal base theory of the Kess-Moody algebra, there is a crystal base of Volmer module, and we also have a crystal base of the integrable Heisenberg module. And the natural projection map sends the crystal base to the crystal base, right? But unfortunately, there is some strange thing happens. The problem is that if we look at the crystal base of the Kess module, and if we restrict it as a module of the UQGL N or U0N, then its crystal lattice is upper crystal lattice. So it is not compatible with the projection. So the crystal for crystal L of K lambda, so especially L0N lambda minus, this part is the upper crystal lattice as a module of U0N, or under the isomorphism psi, it is upper crystal lattice for the UPGLN at P equals infinity. Yeah. So for the upper crystal for the lower crystal lattice for this simple module, the projection preserves the crystal lattice. But here in this case, projection does not sense the crystal lattice to the crystal lattice here. Yeah, that's the difference when it comes to the super case. So let me summarize our situation in the following diagram. So the blue means the lower crystal part, or for GLM or GLM0. And the red or pink part corresponds to the GLN part or U0N part. And this crystal lattice, which appears in the crystal base of the Kess module, is compatible with the projection map from the L infinity for GLM or UM0. But as I just mentioned before, that our crystal lattice for L0N lambda minus is the upper crystal lattice at Q equals infinity. So actually, it is compatible with the dual embedding into the crystal lattice of L infinity. So actually, our situation is as follows. So, okay. So one part you have to think of the the lattice at Q equals 0, and the other part you have to consider the crystal lattice at Q equals infinity, right? And yeah. And okay, so this is a summary of some general facts. And for example, okay, so we can think of so when we want to convert the q equals 0 to q equals infinity, we have to take the bar involution. Okay. And when we want to think of change the lower crystal lattice to the upper crystal lattice, we have to take the dual with respect to some symmetric non-degenerate bilinear form. Right? So here the L infinite and L infinite bar is the correspondence between the q equals 0 and q equals infinity. And also we can take the A0 dual over L infinity, but it is itself. And also we can take the bar involution, not bar involution, it's okay. At q equals infinity, no. For the Von module, when you want to consider the lattice set q equals infinity, we have to take the sigma bar dual bar involution, say sigma. And then they sigma L infinity and L infinity bar are actually A infinite dual. And for the highest weight module, the upper crystal and lower crystal lattice are A0 dual with respect to this bilinear form. So if we want to take the crystal lattice at q equals infinity, then we have to take the still sigma involution, but in this case it is equal to the bar involution. So we have this the crystal lattice. That's the crystal lattice in our setting. Okay. So it's a mixture of, so our crystal lattice is the mixture of these two kind of crystal lattice. So here is a summary. Yeah, so the positive known part that is compatible with the projection, and for the negative known part is compatible with the embedding. So we don't have a compatibility of the crystal of the negative part and the crystal base of the Casimir under the projection, but still we can think of explain a kind of the compatibility, considering another intermediate highest weight module, bigger parabolic volume module with a crystal base. Okay, so let me denote it by x of lambda. So now this part is we just take the limit only to take the limit of the highest weight for the GLM or GLM0. So the corresponding parabolic volume module is like this. So we started from the highest weight module of the GL0n and then extend it as a module of the parabolic, say Q, the extra part acting on the trivially, on this space trivially. Then we can define this kind of module, say x of lambda. Then according to the triangular decomposition, we can say that as a K space, it is isomorphic to the tensor product of our subalgebra K and U minus M0 and the irreducible representation of GL0n. Okay, so this x of lambda lies between the projection from the U minus to K of lambda. And we can prove that this x of lambda also has a crystal base. And then finally we can say that now we consider this kind of map. So if the one is the projection from x of lambda to K of lambda, and the other is the embedding, actually take the dual with respect to the bilinear form. So the embedding of x lambda to the U minus M slash N. Then we can say that our crystal base for this infinite dimensional parabolic volume module is compatible with, and they are mapped to the Casimir module and the negative part. is compatible with the crystal base. So this crystal base goes to the CAS module, and this crystal base goes to our crystal base. Yes, so that's the facts which I can say about the crystal base of the general linearly superalgebra. So it's rather strange, or some facts are not very satisfactory to study the structure of the representation of a UQGLMN, but still something that's interesting happens, I think. So now I have still have 10 minutes. Okay, so I will give some remarks before stop this talk. So first, there is so for the Casimir algebra, there is as a categorification of the negative part of the quantum group using the Quiver-Hackey algebra. So many people are asking, including me, that whether there is also categorification of the negative part of the quantum group even for GLMN. But yes, still not satisfactory answer so far. So even for the Ringel's whole algebra doesn't exist in the super case. But anyway, recently there have been several works to categorify the negative part of the quantum group, and one result is due to the Kovanov and Susan. So they gave a categorification of the negative part of the quantum group corresponding to GLM1. So there is one odd isotropic root, but the CL0N part is trivial. But anyway, so they introduced still the very similar kind of algebra, so called the Quiver-Hackey algebra, but I'm not quite expert in that language, but they consider certain differentially graded algebra version of the Quiver-Hackey algebra, and they consider the differentially graded category for that modules. And then of course, they defined the GLMN case. Those kind of algebra was defined for the GLMN, but for GLM1 case, they show that there are certain differentially graded category realized the negative part of this quantum group. But still, they do not gave for the general case. So it's still an open question. Yeah, basically, in the paper by Kovanov and Susan, since the rank is GLM1, so there is no other set relation. So the main problem is how to categorify the other set relation. That was also remarked in the paper by Kovanov and Susan. They say that it will be more challenging. Yeah. Okay. And also there are some couple of works on the canonical basis of the negative part of the quantum group. So one by actually the Clark and Hill and Wang's paper was there's a published year, so the preprint was I think uploaded earlier than the next one. But anyway, so Clark, Hill, and Wang introduced more precise pseudo-canonical basis. So they constructed, how to say. So in case of super case, it is not. It is very more difficult to think of a Lustig transformation, kind of automorphism. But instead of using the Lustig transformation in superversion, Clark, Hill, Wang, and adopted the approach by Leclerc when he realized the dual canonical basis or canonical basis inside the quantum shuffle algebra. They generalized this approach to the basic classical Lie superalgebra, and then constructed a PBW type monomial basis, and then considered a bi-involution. And then once we have a nice integral unit triangular property, then there is a bi-invariant basis. Then they show the existence of that kind of basis and call it the pseudo-canonical basis. And yeah, and then what is the next question? What is good for that kind of basis? So they define the notion of a canonical basis, and with which when the pseudo-canonical basis has certain more nice properties actually given by the orthonormal property a q equals 0. But their canonical basis, they conjecture that their pseudo-canonical basis satisfies that kind of almost orthonormality. And okay. Yeah, and actually their PBW time monomial is almost equal to our, of course, they consider more general class of PBW basis. And our PBW basis is a special case of that, of their PBW basis, except the fact that actually we apply the dual by involution on the other part, GL0n. Okay, anyway. Yeah, and another canonical basis construction for UMN, not only U minus, is given by Jia and Gu in 15. So their construction is using the quantum Schur superalgebra. So their approach is starting from the Schur duality, and they consider a superanalogue of the Schur algebra, and then they construct certain nice bases there, and then it is compatible with the negative part of the quantum group, and they call it the canonical basis. And in some sense, it has some good property, some compatibility with the basis of the polynomial representations. But anyway, and also it is not known that whether the two canonical bases in 2 and 3 are, how they are related is still not known. Okay, so so the related question is, so we have abstract crystal for at least for gel M1 infinity, and actually there is a categorification by Kwon and Susan. So it is natural to think about. I think it might be interesting to think about the categorical interpretation of our abstract crystal in using the Kwon and Susan's language. And also still my question is whether we still have some nice canonical basis which is compatible with irreducible representation as the crystals. And, yeah, it's of course anyone can ask that question whether there is a categorification for them. I'm not sure whether it is this question makes sense, or it's still, yeah, the conjecture is true or false. I do not know, but anyway. Yeah, so finally, now in the last couple of minutes, let me mention some related works on the crystal base theory for the basic classical Lie superalgebra. So for the QN, the pure Lie superalgebra, in that case, there is a work by the GJKKK, where they show the existence of a crystal base of a kind of irreducible, so-called polynomial representation. And this actually, this polynomial representation also appears as naturally appears from the analog of Chauvet duality. So people call it the Chauvet-Sergeev duality, or it's the Sergeev duality. So it forms a nice semi-simple tensor category, and then in that paper, the existence of crystal base exists, and then and also there are related other papers where that. Using that crystals, it has a very nice application to the combinatorics of Schur people. Okay, and also I'd like to mention that there is then it's another work by, there is another paper by Saban and Travis. So they consider the crystal of the irreducible polynomial representation of Q, and then they find a very nice inductive, how to say that, some certain limit process of the crystal, and they call it a B of minus infinity. So still it's an abstract crystal, but so it would be nice to have an algebraic construction of their abstract crystal, B of minus infinity. And the last comment is the case of orthosymplectic. So it's a mixture of orthogonal and symplectic Lie superalgebra. And yeah, still, the natural representation of OSP and its tensor product. So maybe, yeah, we can ask that. Now we start from the natural representation, its tensor power, whether there is a nice duality to have, so that we can have a nice irreducible representation inside, which may have a crystal base. But unfortunately, it's not, actually the tensor power of the natural representation is not semi-simple any longer. So I do not know whether it has a nice crystal base theory. But instead, I consider another family of the representation, also simplex representation, so-called oscillator representation. And the reason why I consider this kind of representation is that they form a semi-simple tensor category. And why is that possible is that from a viewpoint of a superduality, which was established by Shunjin and Wei-Chang and Engel, then this family of infinite dimensional representation naturally corresponds to the integrable representation, integrable highest weight modules of the classical Lie algebra. So where there is a crystal base theory. And so we have a certain equivalence. So we can naturally expect the natural counterpart on the superduality may have a crystal base theory. So I try to prove it, and then we can show that the certain nice family of tensor, nice family of irreducible representation has a crystal base. So starting from, so using those infinite dimensional representation, now we can think about, now we want to think of the negative part of the quantum group, but we couldn't go directly. So now the current project with the collaborator Zhang and Bruno is now we're trying to prove the crystal base of parabolic Volmer module, and then after that we want to take a limit to the negative part of the quantum group. Yeah, so that topic, the also simplex representation, we also have some I think is some good combinatorial model. So I had a chance to give a talk about this crystal base theory, or not actually crystal base of that, but anyway, for the combinatorial model for this crystal in 2016, February. So I was invited by Professor Ariki to give a talk about that in Osaka Representation Theory Seminar, ORTS, right? So at that seminar, the Professor Okado was there, right? Yeah, you were there, right? Yeah. After the talk, he came to me that your building block oscillator representation is it's already appeared in his paper, and he sent me an email about 3 of his works, and you should look at these papers, and we have some overlaps, and we have to work together. He said that. Then after that, I began to visiting Osaka University very often, and then yeah, so currently we are also working with the affinization of the Q oscillator representation for super cases, and jointly with my students with Shin Myung. Yeah, so at that time, I was trying to, so before that, I was more working on the algebraic combinatorics. And also, of course, I was considering algebraic side, but at that time, I was trying to move my research topic more affine. But by myself, I had many difficulties. But after I began to visiting here, that I actually learned more about the very well-known, even many results before, about the quantum affine algebras and their representation and R matrices. And yeah, so I really was happy to had a chance to give a talk in Osaka representation theory, and to meet Professor Okado and had a chance to work with him and so far. Okay, so that's all for my talk, and thank you very much. Yeah.
Thank you. Are there any questions or comments? That's right.
So if I understand correctly, do you have a crystal structure directly on, I'll call it Lustig data for GLMN?
On very special case of convex ordering, the diagram. This kind of just where is it? Yeah, the Lustig data. Yeah, yes. In this case, yeah.
And and just to make sure that that extends for your B infinity construction as well. Correct? Okay.
Yeah.
Thank you.
Are there any questions? If no, then thanks, speak again.
Yeah.